Hey everybody, this is lecture 18 of Applied Statistics at Bethel University in spring 2020. You could also call this class Advanced Undergraduate Statistics. It is calculus based, though in this lecture you can understand most of it without calculus. I do talk about calculus a little bit, but you can get a lot out of it without calculus if you are needing advanced statistics but you don't know much calculus. It's going to consist of two parts here in this lecture. The first part is going to be a summary of lecture 17, and I'll put a link to lecture 17 in the description below as well as above here on the video. Lecture 17, we looked at a practical example of simple linear regression with just one explanatory variable, and it was a linear model. And I showed a lot of formulas and a lot of answers in that video. The formulas kind of got overwhelming. In this lecture, I want to focus more on the practical interpretations. That's really the more important thing. You know, you can get the computer to give you the output if you need to. You don't have to do the calculations on your own. The more important thing for most people is to be able to interpret the results. And that's what I want to focus on in the first part of this lecture. The second part of the lecture, I'm going to do something pretty different. I'm going to start to introduce multiple regression by considering something called a quadratic polynomial regression example. Usually in multiple regression, you've got more than one explanatory variable. But in this example, we're just going to have one, though it will involve a quadratic function instead of a linear function. I should also say that in the description below, I'm going to put a couple links to Google Drive folders where you can find both the PowerPoint for this lecture and also a Mathematica notebook that's going to have some calculations that we need to do. So let's get into the lecture plan in a bit more detail here. So again, the first part is the summary of practical conclusions from lecture 17. You don't have to watch lecture 17 unless you're really interested in the details of the formulas and the calculation. We're going to focus on the practical interpretation. The situation where we're trying to estimate 2019 tuition using 2013 tuition. 2013 tuition is X, 2019 tuition is Y. We're trying to predict Y when we know X. We'll talk about how to practically interpret the slope and the intercept. We'll talk about the regression standard error interpretation, the standard error of the sample slope, the t-test for a significant regression, which is one of the most important things to do at the start, and a confidence interval to estimate the population slope, a confidence interval and a prediction interval for a subpopulation of schools whose 2013 tuition I picked, my own choice, to be similar to Minnesota State University's, which by the way is different than the University of Minnesota. The coefficient of determination will emphasize its importance in the model based on the fact that in this case it's very close to 100%. Second part of the video, we get into quadratic polynomial regression example. We'll talk about the model and we'll use Mathematica in a pretty interesting way actually. We'll use Mathematica to generate our example essentially. We will essentially know the population and then we will sample from that population in the Mathematica notebook and then do calculations with that sample. We'll also illustrate how to derive and represent the various things that go on in symbolic form. We'll talk about minimizing SSE, the sum of the squares of the errors being synonymous with residuals. The normal equations from lecture 17 do generalize to lecture 18. That, for my students especially, is one of the most important things to get out of this, is what's the nature of the normal equations. We'll write them in both scalar form and matrix/vector form. And then we'll talk about something called the design matrix, which is kind of the quickest way to think about the matrix vector form. All right, let's get into the example. Again, this was tuition at Big Ten schools, and here is a table with the Big Ten universities, all 14 of them, not 10 anymore, where the 2013 is the X value and the 2019 tuition is the Y value. And like I said in the last video, you can see all the 2019 tuitions are bigger than the 2013 tuitions, as you would expect, and not just because of inflation perhaps, but because also they're trying to, in a sense, make more money because perhaps their state support is going down or something like that. All right, so again, the goal is to use this data to predict Y when we know X. Now I should say, and I'll re-emphasize this on the next slide, I think, that this is not a random sample. Okay, this is very far from a random sample of all schools and universities and colleges in the country or the world. And so it's not necessarily representative of what really goes on overall. But we'll go ahead and try to apply regression for inference with this anyway, though we should do it with caveats to realize our predictions might be wrong. And so to have confidence in those predictions, you'd really want to compare it against other data. You'd want to compare it against other schools, both big and small, before you would be confident that it really is giving you good information for inference. Here is a graph of the data points, and we got one big outlier, and that's Northwestern University near Chicago. It's much more expensive than the other Big Ten schools. Though it does fit the trend pretty well, you see the regression line in here, the least squares regression line that minimizes the SSE, the sum of the squares of the errors. And you can have the technology compute the regression line equation for you, and I wrote it like this before. It's probably simplest to write the left-hand side of the equation just with a little y hat to emphasize we're trying to predict y when we know x. The hat just means we're trying to make a prediction or an estimation, again in this case, of a y value when you know x. The other symbols, it's still worth talking about here. In this more advanced statistics class, we talk a lot about random variables. The capital Y emphasizes that the 2019 tuition for any given x could be thought of as a random variable. The vertical line there means given that we know what x is, we know what the 2013 is. That's a random variable, and again the hat means we're trying to estimate a value of that. The mu is the theoretical symbol for a mean. The mean of y given x. You see the subscript, the capital Y given x. For any given fixed x, for any given 2013 tuition, what is the mean 2019 tuition for all such schools? Okay, the mu hat means we're trying to estimate that mean. You can use the regression line to either estimate a mean or an individual value of y. Here's a summary of the practical conclusions of the calculations that were done in lecture 17. But let me re-emphasize, this is not a random sample of all large public universities, and certainly not all universities overall, but we might try making inferences from it anyway. Okay, but just be aware, you got caveats. We would have to compare our inferences against more data from the wider population to have confidence in our conclusion. And more ideally, if you were really trying to make wider inferences about, say, all colleges and universities in America, you'd want a true random sample. At the very least, we can go ahead and do the calculations and compare the conclusions to the actual data from the wider population to see how far off in which direction, too high or too low, the model might be off. All right, let's get into interpretations of the various calculations. Here was the slope that we got. B1, lowercase b1 means this is an observed value of a slope, a sample slope. Capital B1 will refer to the sample slope as a random variable, and I will talk about that here. I think it's in the next slide. In interpreting, it's always important to think about the units. Okay, now the units here are a little weird. It's always units of y per unit of x. The unit of y is $2019 and the unit of x is $2013. And that's not just a label by the year. There's also a meaning with regard to inflation sort of hidden in that. You know, inflation occurs, generally speaking, prices go up over time. Better way to think about that actually is the buying power of your money goes down over time. You need more money to buy any given item on average. And so you really are thinking about this model in what's called real dollars. Well, actually it's nominal dollars, and to compare it to inflation, you'd have to actually think about how inflation is acting from the year 2013 to the year 2019, which I will do here in a minute. So how do you interpret the slope? You could say if one school's tuition in 2013 was about 1,000 more than another school's, then multiplying 1,000 by 1.2 to get 1,200, you would expect the first school's tuition in 2019 to be about 1,200 more than the other school's tuition in 2019. Does that expected difference outpace inflation? Here's a way you can answer that question. You can multiply $1,000 by what's called the ratio of the consumer price index of 2019 to 2013. It's just a ratio of two numbers, where the 2019 is the 255.7, the 2013 is the 233.0. That ratio is bigger than 1. What that's going to mean when you multiply it by 1,000 is it's going to give you a number, which you can see is 1,097, where the buying power of 1,097 in 2019 is essentially equivalent to the buying power of $1,000 in 2013. You can buy the same amount of stuff in general. Now that doesn't apply to all kinds of items. It's an average over many, many items. The fact that that number, 1,097, is smaller than 1,200 means that the increase for these more expensive schools from 2013 to 2019 outpaces inflation. Schools that were more expensive to begin with became even more expensive over time. So that, you might say, sounds like bad news, and in a sense it is. But it's good information to know. That's a practical conclusion that we can make from this model, though again, it's not a true random sample. We'd want to compare it against the wider population to be more confident in this conclusion, or else have a true random sample. Second page of summary of practical conclusions. How do you interpret the intercept? In this case, B0 is negative 0.185, $2019. The intercept is going to have units of y. The slope has units of y per unit of x. The intercept has units of y itself, in this case $2019. What does that mean? Well, it gives you the predicted value of y when x is 0. But wait a minute, that's not relevant here, because tuition, for no school's tuition has ever been $0, at least ordinary schools that we're used to here in recent years. Okay, so it's not a relevant thing. We'd be trying to predict the tuition in 2019 from a school that had $0 tuition in 2013. It is still needed in order to use the regression line equation. We still need it in the equation. It's still part of the model. We still need to use it when we plug in a value of x to predict y. Okay? And sometimes, for some examples, it does have real-life meaning. So be aware of that, and it's worth thinking about in general. How about interpreting the regression standard error? What did it equal? It equaled about 866.1. It's going to have units of y. You can see is $2019. You can see I've got these different symbols for it. Don't let that bother you. S is the letter used in my class's statistics book, which looks like this. It's by Milton and Arnold. S sub E is a symbol used by many statisticians for this regression standard error. Sigma hat emphasizes it's estimating something called sigma, which I'll talk about in a minute here. And its formula is that it's the square root of SSE, the sum of the squares of the errors, divided by n minus 2, with regression involving one explanatory variable. The n minus 2 in that case, when you've got one explanatory variable, is going to be the degrees of freedom. Okay, it turns out to be 866.1. How do you interpret that? Well, recall what population parameter this estimates. It estimates something called sigma. This, in the model, is the assumed constant standard deviation, constant population standard deviation of the conditional random variable capital Y given x. It is assumed to be constant no matter what x is. So in the model, this is in the model, not in necessarily your final conclusions about things based on the sample, you have a population data involving two variables, x and y, and you've got this regression line. It's a straight line. It's a population regression line, and you assume that for any given x, that the variability in the y direction stays constant, that its standard deviation stays constant. You can think about this in terms of the two standard deviation rule of thumb. For the population, for any given 2013 tuition x, or at least values close to x, about 95%, almost all, of the corresponding 2019 tuitions for those schools are going to be within about 2 times the standard deviation, 1732, of the unknown population mean. Okay? So it's a constant standard deviation for the y values, thinking about the y values vertically here, no matter what x is. X is horizontal. That's in the model. When we do regression based on the sample regression line and calculate prediction intervals like we did in lecture 17, and I'll also say the answer here for lecture 18, we don't get the exact same number that gets used for the margin of error of the prediction interval. The 1732 here turns out to be something different, even for 95% confidence. Partially it's because the degrees of freedom is n minus 2, and partially because we're doing a sample we would expect a little bit less certainty. I emphasized that in lecture 17 by the confidence bounds on the prediction intervals being sort of smallest when you're close to the mean of the x values, and as you get further away, the margins of error get bigger. Okay, so you're sort of less certain when you're further away from x bar when you use the sample regression line. I'll again emphasize that here in a minute. We can also use the value of S, this 866.1, to compute other statistics that are going to be to come, again, including prediction intervals whose interpretation is similar with respect to the sample regression line instead of the population regression line. The population regression line is this mu equals beta 0 plus beta 1x. Beta 0 is the population slope intercept, beta 1 is the population slope, and we are trying to estimate that with the sample regression line. Oh, I don't know where my cursor went here. I was trying to get my cursor to show up. Okay, well, don't worry about it here. On to page 3. Here we're thinking of the standard error for capital B1. This is not a typo, that's a capital B instead of a lowercase b. I mentioned before, lowercase b1 is the observed sample slope. Capital B1 represents the sample slope as an abstract statistic, a random variable that comes from a random sample. It's got a distribution even. And in fact, based on the model, the model that we talk about, the distribution actually ends up being a normal curve, centered on beta 1, the population slope, and having a certain amount of spread measured by a certain standard deviation that is estimated by this standard error. Sigma sub B1 is the standard deviation of the distribution of capital B1, sometimes called the sampling distribution. It's approximated by something called the standard error of B1, and I showed the formula in lecture 17, and the answer turns out to be 0.025. This is a standard error for a slope, and therefore its units are $2019 per $2013, units of y per unit of x. What does it mean? It's an estimate of the variability when taking random samples from this population. In other words, if we took many, many random samples of the same size, in this case n, actually I forgot what n was. N was the number of data points, but I forgot what it was. It might have been like 14 or something, I think. Yeah, I guess it was 14 because it was the Big 10, which is 14 schools right now. If we took many, many samples of size 14 from the bigger population, not just the Big 10 schools, but the bigger population, and they're truly random samples, this number, SEB1, will hopefully be pretty consistently close to 0.025, and it would be a measure of the variability in the value of B1 from sample to sample. You could use the 2 standard deviation rule of thumb again. You could multiply it by 2 and get 0.05 as being approximately how much variation typically to expect in the values of the sample slope B1 over many, many samples. That's a theoretical idea that's pretty important. It's got some practical importance in terms of deriving formulas for these things and doing hypothesis testing, for example. A t-test for a significant regression. Beta 1, remember, is the population slope. The null hypothesis is that it equals 0, and the alternative is that it's non-zero. Two-tailed is the typical thing to do. And it turns out the t-statistic is pretty big, about 48 with 12 degrees of freedom, and the p-value is super microscopically small. We definitely have a very significant regression. The value of x is definitely of help in estimating both the mean of the y and the individual values of y. And we are not wasting our time, okay, by using regression. If you were not able to reject the null hypothesis in this situation, you might say, well, is this regression even worth doing? Are we wasting our time? 95% confidence interval to estimate beta 1. We did in the last video as well with formulas, and it turns out to be this thing. Focus on the interval form of it from 1.15 to 1.26. The units would be $2019 per $2013. We not only have strong evidence that this is a non-zero slope, but we even have strong evidence that the slope is bigger than 1. And being bigger than 1 does effectively mean, that the 2019 tuition is going to be bigger than the 2013 tuition for the wider population, if this is truly representative of the wider population. That would be the practical interpretation of that. We can do a 95% confidence interval to estimate a mean. We can also do a 95% prediction interval to estimate an individual outcome. Again, as in lecture 17, I went ahead and picked x to be 7681, and I picked this number based on a little bit of research because it seemed to represent, based on what I found, the average tuition of Minnesota state schools. I live in Minnesota. Back in 2013, these are, by the way, in-state tuition numbers. They're higher for out-state tuition. We're trying to estimate among all schools, all universities, whose tuition in 2013 was roughly the same, okay? There may be no other school that has a 2013 tuition exactly the same as 7681, but roughly the same, say between 7650 and 7710 or something like that. What's the mean of all their 2019 tuitions? That's the practical interpretation of this. We can get a point estimate from the regression line itself, plugging in x equals 7681, but then we want a margin of error. The interval estimate turns out to be this. So from 8609 to 9843 in 2019 dollars would be an interval that we're 95% confident, we're pretty sure, contains the true mean 2019 tuition of all schools whose 2013 tuition was close to 7681. Okay, that's probably the best way to interpret that. Again, it's not a random sample, so we'd have to compare with reality to see how well it does to have confidence in our model. On the other hand, a 95% prediction interval estimates the next observed value of the random variable. Why, given that little x equals 7681, this entire thing here represents one quantity, and it's a random variable, it's an unknown thing, it's got a distribution. So here's the answer for that, and it is a bigger interval. What's the meaning of it? Again, I'm wondering about the 2019 tuition for the next university that I pick from the wider population at random that had a 2013 tuition that was roughly the same as 7681, again, maybe from about 7650 to 7710 or something like that. This interval estimate is what we get. It's bigger than the interval estimate for the confidence interval to estimate the mean, as you would expect, because the mean has less variability than individual outcomes. Yeah, 7241 approximately to 11,211 would be your interval. That's probably too many significant figures. And it's a pretty wide interval. So, you'd probably feel pretty confident in that, but again, you'd have to compare it against actual data. Notice that the margin of error, about 1986, is larger than, though you might say the same order of magnitude or the same ballpark as, the 2 standard deviation amount 1732 from page 2. I really want my cursor and I don't know why it disappeared. This 1732 right there. Okay, down near the bottom here. That was the 1732 was the 2 standard deviation rule of thumb when we were thinking about the population. Okay, the deviation from the population regression line. This prediction interval is not constant in its margin of error. I picked x to be 7681, so I have something specific, but if I picked a different x, I'd get a different margin of error. It wouldn't necessarily be 1986. When x is equal to x bar or close to it, that's when the margin of error would be smallest, and when x is further away from x bar, then the margin of error ends up being bigger. It is in the same ballpark, but it's bigger as you would expect, because we're talking about looking at sample data and a sample regression line. That extra amount of bigness sort of gives us more cushion to still say we're 95% sure that we are in that interval. We also saw that the coefficient of determination, R squared, is very close to 100%, 99.48%, and R itself, the correlation, was also 0.99 something, I think. Yeah, it would have to, because R squared would be a little smaller. So that's just telling you that this is a very strong linear trend, and we saw that with the original graph. Those points were practically almost exactly on the regression line. SSE, sum of the squares of the errors, though above 1 million we saw in the last lecture, it's still small compared to SSR and SST, sum of squares of regression and sum of squares total. Those numbers were in the billions. The regression line explains almost all the variation and why there's very little bit of random variability above and below the regression line relative to the scale that we're talking about. All right, that's the end of the first part of this lecture. Now we're moving on to the second part, the quadratic regression example. We're going to look at an example, and then we'll use technology, Mathematica, to do computations with the example. And then we will do a little bit of generalization, though it's not a full generalization of what goes on in multiple regression. So we're going to start by using Mathematica to do a simulation, essentially. Simulate an appropriate data set where we will actually know the polynomial model that the statistics are designed to estimate. We're actually going to know mu as a quadratic function of x. and then we're going to add in some randomness to represent the residuals, so to speak, above and below the regression parabola in this case. That's why it's a quadratic regression, is because the graph is going to be a parabola, it's going to be a quadratic function. The known model that we use is based on just something I picked somewhat randomly. This model right here. Mu sub y given x is a quadratic function of population parameters beta 0, beta 1, and beta 2. Beta 0 is the constant term, beta 1 is the linear term times x. Beta 2 is the x squared coefficient. And I picked these particular numbers. Beta 0 is 13, beta 1 is -4, beta 2 is 0.5. Why did I pick them? It was somewhat random. Okay, I could have picked different numbers. I'm going to take the x's, that's going to be for my sample data, to be some fixed numbers. I picked 0, 2, 4, 6, and 8. I could have picked different numbers. I picked them to be evenly spaced here. They didn't have to be. Okay, I just picked these 5 numbers. This is not really a random sample. I'm thinking of the x's as being chosen. The corresponding y's are going to be generated randomly. I'm going to generate the yi's as random variables for each xi by assuming that yi is the mean, mu, plus capital EI, where EI is a random variable, and I'm going to pick it to have a normal distribution with mean, mu, and variance sigma squared, which turn out to be, I'm going to pick 0 and 2 squared is 4. By the way, with this notation here in this class, we always do n mean comma variance, though I should warn you that other classes, they might do n mean comma standard deviation. And in fact, Mathematica does the mean comma the standard deviation. Okay, so it's different than what I'm doing here with this notation. I'm doing the mean and the variance. The variance is 2 squared, which is 4. The standard deviation is 2. All right, so let's go to the Mathematica. And again, you can try to get things out of this even if you don't know or have Mathematica. It's still worth listening to and thinking about here. So here is my function mu of x. It's a quadratic. Mu of x is x squared over 2, which is 0.5 times x squared minus 4x plus 13. Again, that's the same thing that I picked right here. I can enter that function into Mathematica, and then I can do this quadratic data. Okay, now I'm about to show you quadratic data and a fit for that quadratic data that's not going to match what I have in the PowerPoint here. It's not going to match the equation you see here and this graph here. Okay, and the data is not going to match this one. That's because every time I use this code here, it regenerates random numbers. I'm going to be sampling from a normal distribution with mean of 0 and standard deviation of 2. Remember, Mathematica does a standard deviation there instead of a variance. X going from 0 to 8 in increments of 2 is what this means. But I'm going to get different numbers than I have in this PowerPoint. Just realize that, okay? It's okay. You don't need to have the same numbers as I have in the PowerPoint. In fact, that's a good thing. In fact, every time I enter this, I get different numbers. There we go. Every time I enter this, I get a different set of data. That's okay. Okay? In fact, in a sense, it's good for the purposes of simulation. Fit will actually find the quadratic curve of best fit for any given data set. And for this particular data set right here, it gives me this quadratic. And then I can plot it in this picture. Now the plot that I'm going to generate here will not match the plot here. And the labels that I have here and here, well, just right here at least, will be then wrong. And in fact, I have to copy and paste this new quadratic in right here. And this label will be wrong here, and I'm not going to bother changing it. And what I have then is a picture of the population quadratic in red and the sample quadratic in blue. And again, this equation for the sample would be incorrect now. It's really going to involve this instead. The blue quadratic is really following the sample data better. That is the quadratic curve of best fit for that sample. But the sample itself was generated from a population quadratic. Okay, these numbers, 13, -4, and 0.5, are beta values. These other numbers up here the 8.6, the negative 1.24, and the 0.018 are sample observed values B0, B1, and B2. Okay, and again, the labeling would be wrong here. But that's the idea of what I did. I just wanted to give you that idea. So let's go ahead and look at what we got from the original data that I did when I ran that code. I generated a random sample of size 5, and I got these data right here. Okay, that's the data that I got when I made the following graph. So Fit and Mathematica went ahead and calculated this regression equation for me. Hey, there's my cursor. And here was the corresponding graph I got for these data and this equation. Again, this is sample data, random sample data. The random variate and the normal distribution generated this random sample data for me. Again, coming back here, right here, this is the deterministic part of the model, that's the mu, and this is the random part. In effect, this is kind of like the sigma, thinking of sigma as a random variable. The random variate normal distribution adds on a random term from a normal distribution with mean 0 and standard deviation 2 onto the original x output when we plug in x equal to into mu. So this again is what I got from my first run of it. Now I'd like to talk about the details of how this graph in blue is computed. The red graph was given, that's mu. The blue graph was computed from the sample data. How is that computed? Just like with simple linear regression, we're trying to minimize SSE, sum of squares error, as a function of the unknowns B0, B1, and B2. We'd like to find the sample coefficients B0, B1, and B2, B0 being the constant term, B1 being the x term, and B2 being the x squared term. That's going to minimize SSE, the sum of the squares of the errors, which are also called residuals, vertical distances between the points and the parabola, where when the points are below the parabola, that vertical distance is thought of as negative. The formula for SSE, in my example, my first example that I ran, not the example that I showed you a few minutes ago, has this crazy formula. SSE is a sum of squares of errors. You can see the sums, the plus signs, you can see the squares, and all the things inside the parentheses are errors. They are the y values, like the 14.4595 is a y value. It's the first y coordinate to this point here, minus what you get when you plug the corresponding x value into the unknown quadratic function, b0 plus b1 times 0 plus b2 times 0 squared. X is 0 for that value of y. This next one, the 8.80713, comes from this point right here. You can see its second coordinate is 8.80713 when x is 2. Notice that I'm subtracting what I get when I plug 2 in for x into the regression equation, the sample regression equation, with b0, b1, b2 being unknown. Keep doing that for all 5 points. This function simplifies to this. I use Mathematica for that. And we want to take partial derivatives of that. This is where the calculus comes in. And set them equal to 0 to give our system of normal equations that we'd want to solve for b0, b1, and b2. Now, if you don't know calculus, it's okay. If you do know calculus, I will say it's actually easier, rather than expanding this all out, if you had to do this by hand, it's actually easier to differentiate the unsimplified formula for SSE rather than the simplified formula, because you don't have to spend the time trying to simplify it. And taking the derivative of this is not as hard as it might look at first. It's worth you taking the time to check that this is the system of normal equations for b0, b1, and b2 that we need to solve for b0, b1, and b2 to find them. This is equivalent now, here's where the linear algebra comes in, to a matrix slash vector equation, this one right here. This is the 3 by 3 coefficient matrix. Notice the numbers 5, 20, 120, etc. 5, 20, 120, 20, 120, 800, 120, 800, 5, 56, 64 are the numbers in this matrix, this 3 by 3 matrix, times a 3 by 1 vector, column vector, b0, b1, b2, those are the unknowns. If you know how to take a matrix times a column vector, you can double check that when you multiply this matrix times this vector, you get another vector whose components, whose coordinates are these three expressions on the left-hand side of this system of equations. And that set equal to a three-dimensional vector that is the right-hand sides. These numbers, the 48.2, the 193.5, and the 1323.7 are over here. So we can think of this as a matrix vector equation that we can solve using linear algebra. You can either do row operations, and in a sense that might be the quickest way if you had to do it by hand. You also can write it in an abstract form, and assuming A is invertible, which it will be, you can write the solution in an abstract form for B, the vector B having components B0, B1, and B2, is A inverse times C, where C is the right-hand side numbers for the equation. C is this vector over here, the 48.2, the 193.5, and the 1323.7. So we can represent it symbolically like that, and then we can use technology to solve for B. Calculators can do this, Mathematica can do it. However, I should say, as a word of warning, even with technology, we should be cautious because the matrix A is often ill-conditioned, which basically means that small errors in the entries of capital A can lead to relatively large errors in the solution for B, even with technology. You might say especially if you're trying to program it from scratch. Maybe a program like Mathematica or MATLAB, or if you use R, would not be so subject to this, though I still would be cautious. What does Mathematica give? It gives B to be this vector, and I'll show you how to use Mathematica here in a minute for this. B0 is 15.36, B1 is negative 5.7562, B2 is 0.72 approximately. Those are the same numbers that I had a couple slides ago. Let's see here. Go back a couple slides. Oops. Yeah. 15.36, negative 5.76, and 0.72. I got it here and here. Those are the same numbers. Okay? So you can do it with technology. You can do the matrix algebra. Let me go ahead and show you how to do it in Mathematica. My students need to be able to do this. So again, this was the original data. It's not this new data. And it's not going the original data is not going to be in this notebook when you either get it off of Google Drive or for my students when they get it off Moodle. By the way, here is a way you can minimize SSE in Mathematica. You can take these partial derivatives that you see here and set them equal to 0 to solve for B0, B1, and B2. But again, this is different data, so you're going to get a different answer. Those are different numbers. Although, oh no, actually they're the same numbers because I used the data that I got in the first round here, 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 and here. So these are the correct numbers that I got from the first round. We can solve it on the matrix level in Mathematica. A is this right there. That's a 3 by 3 matrix. I can take the inverse of A and multiply it times the C vector and see the answer. Those are the same numbers that I had in the PowerPoint. So again, my students should be able to do that. If you're not one of my students, if you have Mathematica, you can try it. If you have MATLAB or R, you can try it on those as well. Just 2 more slides, I think, here. Continuing example, the example for quadratic, the quadratic example. This is, for my students especially, this is the most important slide, actually. The matrix A from the previous slide can be computed using a trick. And this trick has some reasoning behind it, which we'll talk about in a future lecture. You can let capital X be something called a design matrix. In our book, it's also called the model specification matrix. But I'm just going to typically call it design matrix. And then let the A matrix be X transpose times X. The T means transpose, where you swap the rows and the columns. Effectively, the first row becomes the first column, the second row becomes the second column, the third row becomes the third column of X to make this new matrix X transpose. But what is X? It's this matrix here for this example. And this is a fairly simple matrix to make. It's got 3 columns because there are 3 unknown parameters we're trying to estimate, beta 0, beta 1, and beta 2. And then it's got 5 rows because we've got 5 data points. The numbers in the first column are always 1s. The numbers in the second column are the x values. x1 was 0, x2 was 2, x3 was 4, x4 was 6, and x5 was 8. And the numbers in the last column are the squares of those x values. This is x1 squared, x2 squared, x3 squared, x4 squared, and x5 squared. And it simplifies to this. If you take the transpose of this and multiply it times itself, here's x transpose. I swap the rows and columns. X is a 5 by 3 matrix. Its transpose is a 3 by 5 matrix. Multiply that by x, you get a 3 by 3 matrix. A 3 by 5 matrix times a 5 by 3 matrix is a 3 by 3 matrix. You should know that from linear algebra or maybe even college algebra. You might have had that kind of thing. It's a 3 by 3 matrix, and notice this is a special 3 by 3 matrix. It is capital A that we got before. Though I guess I didn't have it in the PowerPoint. It is this A right here that I have in Mathematica. And amazingly, you can also calculate that A using summations. And actually, this code is going to produce the wrong answer because it's based on this new data. So if I enter this code, I'm going to get a different matrix than this one. Oh, wait a minute. It does look like it's the same matrix. Maybe I still have the original quadratic data stored. Sorry about the confusion there. Looks like it is still the same matrix. But it will not be when you try to enter it if you try to go through my code one by one. That is, again, something called the design matrix. And again, the A, where am I? Here we are, sorry about that, is computed as x transpose times x. Moreover, C, the numbers on the right-hand side of the A, B equals C equation is x transpose times y. There's the transpose of x. Here's y. These are the second coordinates of the data. y1, y2, y3, y4, and y5. A 3 by 5 matrix times a 5 by 1 matrix column vector gives you a 3 by 1 matrix, a column vector. And those numbers, again, are the coefficients that I called C here. Those are the right-hand side of the normal equations, excuse me. These are not B0, B1, and B2. It's the right-hand side of the normal equations. Again, I need to solve this system to find B0, B1, and B2. And that's what I did with the Mathematica. In general, this is our last slide here. In general, the design matrix and the normal equations for a quadratic model based on data x1, y1, x2, y2, etc. through xn, yn, for us n was 5, are as follows. Here's the design matrix. First column is all ones. Second column is x1, x2 through xn, the first coordinates of all the data points. Third column is those numbers squared. Take x transpose times x, and you get the matrix I called A, which is the left-hand side of the normal equations. That is not shown here, simplified. I'll show you in a simplified formula in a minute. That has to equal the right-hand side of the normal equations, which can be found as x transpose times y. So over here, this is the left-hand side of the normal equations, x transpose x times b. Over here, this is the right-hand side of the normal equations, x transpose times y. The left-hand side does simplify the product of these two matrices to this matrix, this 3 by 3 matrix. The upper left entry is n. For our example, that was a 5. These two entries, entry on row 1, column 2, and entry on column 2, row 1, row 1, column 2, and row 2, column 1, are both the sum of the x's. The entries along this off diagonal are all the sum of the x squareds. These two numbers are the sum of the x cubes, and this is the sum of the x to the fourth. That's pretty amazing. Moreover, and you should double check that by actually imagining multiplying these, by the way. Moreover, if you simplify the right-hand side, multiply this matrix times this column vector, it simplifies to a first entry having the sum of the y's, second entry having the sum of the x times y's, third entry having a sum. It's equal to the sum of the x squareds times y's. You should double check that with the example. The Mathematica here. This is the matrix. For example, 5 is let's see, that is n. N is 5. The 20 is the sum of the x's, which would be 0 plus 2 plus 4 plus 6 plus 8 is going to be 20. Yep, double check that in my mind. The 120 is the sum of the x squareds. So take 0 squared plus 2 squared plus 4 squared plus 6 squared plus 8 squared. That's going to be 0 plus 4 plus 16 is 20 plus 36 is 56 plus 64 brings you up to 120. And that's the number that you see here and also here. Okay, you can check the 856.64 as well. So you can find those normal equations here by doing summations. Okay, and this does generalize to cubic models, quartic models, and it also generalizes to multiple regression where we've got more than one independent variable. And those are the kinds of things we're going to focus on in future lectures. Thanks for watching.